Right, when we're dealing with weak acids, we're talking in general terms about ones that are not fully dissociated when dissolved in water. And as a general rule, these will have a high Ka or a low pKa value the stronger the acid gets. So if you see a value of a Ka which is very high, then that indicates that the weak acid is a particularly strong one. Of course, with weak acids, these are nowhere near as strong as strong acids, because strong acids, of course, are fully dissociated, whereas weak acids are not. Right, HF is a weak acid because the bond between the H and the F is very, very strong. This means that less H plus ions are available to be released compared to, say, HCl, which we classify as a strong acid. And this is important because a lot of people think that HF is a strong acid because it's in the same sort of group as HCl and HBr, which are strong acids. But HF, of course, is a weak acid due to the very, very strong nature of that bond. And remember, with covalent substances, the smaller the atom, generally the stronger the covalent bond will be, because the distance between the shared pair of electrons and the nuclear charge is very small, therefore giving a strong attraction. Right, with carboxylic acids, things get a little bit more tricky, because these acids get weaker as the chain gets longer. So the extra carbons that you get by increasing the chain length produce an electron releasing effect, which makes the resulting carboxylate ion less stable, so therefore less likely to form, making dissociation less likely, and therefore the acid is weaker. It just means that they're less likely to produce a proton because they are less likely to break apart due to this electron releasing effect. So as you can see with the ones on the screen, the pKa value is getting bigger as the chain length increases, and when you increase pKa, the acid gets weaker, unfortunately. Right, the next example, when we're using these carboxylic acids with halogens attached, they play an important role because these acids get stronger as the more electronegative atoms are added to the carbon chain. So if we start on the left hand side, we've got very basic methanoic acid, which has a pKa of 3.75, and then as we start to add halogens into the carbon chain, the pKa value decreases sharply. The middle one with a pKa of 1.35 is stronger, and then the end one with 3 fluorines is very strong with a pKa of 0.23. Again, all weak acids, but the stronger one is the one with the fluorines involved. And the reason for this is because the acids get stronger as more electronegative atoms are added to the carbon chain. So these electronegative atoms withdraw electrons towards themselves, which causes the OH bond to become weaker, meaning the acid is stronger and the pKa is of course lower. Right, dealing with bases now. Generally, the bases that you'll deal with in the AQA syllabus will tend to be amines and ammonia. What happens with these is very simple. The reason why they're able to act as bases is very simply because they can accept a proton in terms of Bronsted-Lowry by donating a lone pair. So as you can see here, this is an amine, and then in comes the H+, and the amine is happy to accept the H+, because it's going to donate the electrons and form a coordinate bond to it. So by definition, in this case, the amine is acting as a base. And they will do this quite readily all the time. So that's why we classify amines as bases. Now, what we also need to know is how stronger bases can be sort of determined by just looking at the chain length and looking at what atoms are involved. Now, as a general rule, we use pKb to represent the strength of a base. Now, looking at the table on the screen, ammonia has a pKb of 4.75, and then as we add a carbon to the ammonia to make methylamine, we get a pKb of 3.36. Now, the lower the pKb, the stronger the base is. So by adding a carbon to the nitrogen, we've actually made the base stronger. The reason for this is because of the electron releasing effect of carbons. And what that does is when you have the electron releasing effect, the electrons from the carbon are pushed towards the nitrogen, which makes the lone pair that's on the nitrogen get pushed further away from the atom, making it more readily available, hence a stronger base. Now we can see this effect is furthermore when we have two methyls around the nitrogen in the third example, and this shows the electron releasing effect is almost doubled, and as a result of that the pKb drops down to 3.27. An unusual example is the bottom one where we've got the phenylamine. So you've got an NH2 attached to a benzene ring. Now this has a very, very high pKb, which indicates it's a very, very weak base. And the reason for that is that the lone pair on the N becomes involved in the delocalized benzene ring structure. And as a result of that involvement with the delocalized benzene ring, that lone pair is no longer available to be donated. Therefore, that nitrogen atom is highly unlikely to accept a proton and highly unlikely to act as a base. So therefore, we sort of classify it as being a very, very weak base as a result of that. Right, okay, so we're taking a little look at conjugate acids and bases now. This is an area where people often get confused and they're not quite sure what the examiner's asking of them when they get to this section of the exam. The idea of conjugate acids and bases is based on the idea of the equilibrium that you can see on the screen in front of you. So what we've got here is ammonia and water being reacted together, and they're producing an ammonium ion and an OH minus ion. Now when you look at this, you can see quite clearly that the NH3 is gaining a proton and therefore is acting as a Bronsted-Lowry base. Now the water is donating a proton. It starts off as H2O but has now become OH minus, so therefore by definition the H2O is acting as an acid because it's donating its proton. Now the confusion comes when people start talking about conjugate acid or conjugate base. Now the conjugate acid is very much the species formed after the base has gained a proton. So in this case the ammonia is the base, it's gained a proton and it's become NH4+. NH4+ is the conjugate acid. So just to recap, the conjugate acid is the species formed after the base has gained its proton. And then conversely, a conjugate base is the species formed when the acid has lost its proton. So in this case, you've got water losing a proton to become OH minus. We know that the water is acting as an acid, so therefore the OH minus is the conjugate base, because this is what the acid has become after it's lost its proton. And that's very, very important. The conjugates are just what is produced after loss or gain of the proton. And that's very simply what it is. The idea is that you'd notice in this example that ammonia is the base, water is the acid, the NH4+ is acting therefore as a conjugate acid, and the OH minus is acting as a conjugate base. Right, in these examples on the screen there are quite a few different ones. We're just going to go through which ones are the acid, which ones are the bases. So in the top example it's a fairly straightforward one. The HCl is the acid and the H2O will act as the base. I know this because the HCl on this side is becoming Cl- and as a result is therefore losing a proton. The water is gaining a proton to become H3O+, therefore acting as a base. Now on the next example, the ammonia is acting as a base and the water is acting as an acid. You can see that because the ammonia from NH3 turns into NH4+, therefore gains a H+ ion, therefore is a base. The water losing a H+, becoming OH-, therefore an acid. And as we go down to number 3, the HCl is an acid because it's going to lose its proton, and the NaOH is a base because it's going to gain a proton. And the reason why we know this is because the HCl will break apart to give Cl-, therefore losing a proton, and the OH will accept a proton to become water on the right hand side. Right, the next two are a little bit more tricky, but if you use logic you can kind of figure out what's going on. So the CH3NH2 is becoming CH3NH3+, therefore must have gained a proton, therefore acting as a base. The HCl is losing a proton to become Cl-, therefore must be acting as an acid. And the bottom example with the ethanoic acid and the water, fairly straightforward. The ethanoic acid is turning into the ethanoate ion, therefore it must be losing a proton, therefore it's an acid. And the water is accepting a proton, therefore acting as a base. When it accepts that proton, it becomes H3O+.